Okay, we can start now. Hello everyone, thank you for coming for today's session. Today we have Ericson. He's a PhD student here. He submitted his thesis recently and still waiting, and he's also a structural engineer at EPStruct, and today he'll be talking about the manual development of 3D model challenges, tools, and strategies. Thank you, Ericson, for presenting. It's all yours now.
Awesome. Thank you, Bhavan. When I started thinking about what to do in this presentation, I think it was a really cool thing if I could speak about manual development of three-dimensional models, especially because it's really painful. And after fighting a lot with it, I think I got a good grasp. So I started my PhD in 2013 about wall-to-floor interaction with forced concrete buildings. That's pretty much three-dimensional interaction produced by the floor slab when you consider in-plane and out-of-plane stiffness. So it ends up coupling the response of the walls at the same time with the columns. So it ends up working like a kind of a frame, but a weaver frame. So I started modeling in OpenSees in 2014. I started using my first code was in Navigator. And since then, I've seen really great developments in GUIs and UIs like ECs and STKO. But at the time, I didn't know them, and I thought, I thought that it was really the coding OpenSees Navigator was really static, and it was hard coded. So I wanted something where I could use all the full potential of the program languages, and that's why I started coding in Tcl. And I fell in love with the language. It's really cool, and one of the main things that I like is the fact that everything is a string. So it just depends on how you interpret that string. It takes the form that you want. So that's really flexible. But I also use Python for all the data analyses that are really complicated, especially in OpenSees, because you have, when you create a recorders for the whole building, you end up with tons and tons of text files, and each text file is really huge. And then I use Excel for simple things, small visualization things, because it's faster. My talk today is mainly concerned about the versions 2.5, OpenSees and OpenSees SP, which was the ones that were available when I was doing my models. And then recently I had the pleasure to work with version 3, but I think that was a temporary version. I think it was never released. If you get to any of my scripts, you will see that I use Spanish because it's my first language. So I use Spanish for variables and functions. That way I don't get confused. And then English for coding and comments, so everyone can understand it. As I said at the beginning, this presentation will be mainly focused on manual modeling rather than the results that I've got from my models. But I anyway included some of them to see what's going on with this three-dimensional interaction. So what I'm going to model is this building. It's a wall is in the, not in the transverse direction. It has walls. Those walls are really long. They are about 12 meters long, and the building has 7 stories. And in the longitudinal direction, it has moment frames. But since the columns, as you can see, are really close to the wall, especially in grid lines 320 and 330, that was a really interesting thing to see because of the stiffness of the slab at that zone. So that's why we selected this model, this building. The building mainly comprises a double T floor system, so suspended ceiling. Between grid line 310 and 320, the distance, well, all the distance 310 to 320 to 330 to 340 is about 15 meters span. And then in the longitudinal direction, every grid line is spaced at about 8.4 meters. So overall, it's about 50 by 44 meters footprint building, and it's about 30 meters tall. The wall as well is, it has a really heavy reinforcement in the boundary areas. from the end of the wall until this part here, which is the confined part, the confined boundary area, it measures 2 meters long. So it's a really long boundary area. And also the reinforcement is quite big. 3HG-25 spaced at 100. And heavily confined as well with the series, HD-12 at 150. So it's a really ductile wall. The elements, so the main thing, since I'm modeling the floor, I need to really capture or model what's there. So the floor is 500 double T units with 100 millimeter topping and reinforcement in both directions. So kind of a mesh. It's not really a mesh, but it's a net of reinforcement, HD-12 at 300 each way, and it has saddle bars and starter bars to cover all the negative moments that may happen. It also has, in this part here, between grid line 320 and 322, it has a cast in situ slab that is 175 millimeters thick. The longitudinal beams are that section, and the double T's are web seated on the ledge of the beam. And the columns are 800 millimeters in diameter, and they're also quite heavily reinforced. So in order to model this building, I based my considerations on previous research. From the 1980s, it has been some research that has dealt with the three-dimensional interaction of different elements, like the US-Japan collaborative research in 1985, and then the shape table test in 2007 in UCSD. So based on this research and some numerical research as well, I needed a three-dimensional model, so I could account for the response of the floor, mainly not mainly, but in plane and out of plane direction. Then for the wall, I need a plastic hinge model that could account for variations in axial force. Just because of these elements couple, the slab couples the response of the walls and the columns, there are internal forces, redistributions that affect the axial forces of all the elements. So it was quite important to have a plastic hinge model that was able to capture that. And then second, that plastic hinge must account for axial elongation as well, which is a topic that it's not really modeled, and it's not the concern of anyone. Only the New Zealand standard has some clauses for elongation of different elements, but not in the rest of the world. But we knew that was a really important thing. And also we knew that if, as you can see in the pictures on the left-hand side at the bottom, when the wall bends, one of the ends lifts, so that picks up the slab, and that's what generates the coupling of everything there. So we really need something that if the wall is going to elongate, I need to capture that elongation in order to model the real behavior of the wall and the real interaction with the floor slab. And then the last one, since I'm going to work with a three-dimensional model, something that is really important is to have an appropriate loading approach. So I don't generate spurious loads or unreal stresses in any of the elements. So the first part, I will address it as challenges. So it will be like challenges first part, and then how I solve it, the challenges second part, and how I solve it. So this first part, when you use commercial software, it is quite kind of easy to just draw lines, draw elements, and then you have mesh schemes that you can use, mesh tools. For example, in those two screens at the top are from EDAPS, and whatever you draw there, you can just mesh them. And then you don't even need to be concerned about continuity or connectivity of the elements, because with the auto line constraint option on the far right, you can solve that immediately. But for example, in OpenSees, we know that that's not possible. And actually, in this case, for example, if the blue element goes from the blue node to the blue node, and then another element, the green one, goes from the green node to the green node. If that node is not shared between the two elements, they are not connected. Same thing happened with shell elements. So OpenSees doesn't have a GUI that helps you to see these things, and it was really important to have the appropriate continuity connectivity between the elements. Then another challenge is to work with units, because OpenSees, as we all know, doesn't have units. Well, it has units, you just need to be consistent, but there are no predefined units. And that's quite tricky with materials. And the one that I'm aware of is bonus PO1, that when you call it and you put kilonewtons and meters or any SI system, it tells you that the storm penetration model has to be modeled in KSI and inches. So that, for example, depends on the material, sorry, on the units, and you have to work in the right units. Otherwise, it will give you just nonsense. The other one that is important is the zero length section element, because since it is a zero length section, that element has a unitary length, and that means if your model is in meters, then your unitary length will be meters. If your model is in inches, then that unitary length will be in inches. But the thing is that the section will have the same sectional response against moments. So you will have the same curvature, but with different length. So you will have different rotations, and that affects the whole model. The third challenge was how to load this structure, because we wanted to be as accurate as we could. And that means that the distributed loads for the areas are something that is really important. But as you can see in the wiki page, continuum elements do not accept element loads. So it was necessary to create something to load all the elements. And obviously with a model this size, it's impossible to do it by hand. So I had to find a way to do it. And then the last one is the adaptive solution approach to address non-convergence. That, as anyone knows that is working with OpenSees, we have this typical code in which we analyze for one step, and then you save the output of that in the variable k, and then we check if that converge. If it doesn't, then we try to change the algorithm or any other thing, and we keep changing and we keep changing. So every time that we want to include a new algorithm or a new strategy, the code gets longer and longer and longer. And then it's really difficult to reuse it or even read it. So it's just static and it's difficult to read, as I said. So I wanted to address that. So in order to address that, the first thing, so I work on steps. The first step was to define the global and local reference system. So it is consistent and I can work without worries that my elements will be oriented in any random orientation. Then the base units. Then I create the primary nodes and the labeling of them, the support conditions for those elements. And then I create the elements, and the elements will be responsible to generate all the secondary nodes that the model needs in order to be connected with everything. Then I load everything, then I create analysis. So in my case, since we normally work with two-dimensional models, and that means X and Y, and we normally take Y as vertical. Well, I normally take Y as vertical. So when I move to three-dimensional space, I just keep the same orientation of X and Y, and just I aggregated the Z axis. So that's why that's my global reference system, or the orientation of the global reference system. Then I wanted to have the less geometrical transformations as possible, just to make the model easier. And in order to do that, I define my local axis. I always, when I define an element, a beam column element, I always define it in the positive direction in whatever axis it is oriented. So for example, in this particular case, it's parallel to the x-axis. Therefore, the first node I will be closer to the origin, and the node J will be far away from the origin. and then I will select the vec xz, so z axis is horizontal. So I try to do the same thing for the rest. And for shell elements, it has to be defined counterclockwise. So I define it as IJKL, and that defines the local reference system of that element as the 3 arrows that you can see there. Then the base units, I expanded the lib units TCL file, and I created a function. So, and I would like to show that function. So this is the function and the procedure, as it's called in OpenSees. And if I want to put a unit, I will just call, and I give the names that I want. So then those are the force unit. And for example, if I say 1 inch, it will transform that inch into meters, which is the base unit. But now I can do exactly the same. Let's say that I'm going to work in inches. So I can just change the units of the model just like that. And when I say, what's the value of 1 inch now, it will tell me 1 because I changed the base units. So in that way, this procedure can handle, you can write a script, for example, in whatever unit you want. And then if you put a bone slip model that you know that you need KSI at inches, just go at the beginning of the script, change the base unit, and since everything is defined based on units, you don't need to do anything else. You need to have 2 files. You don't need to have or modify the lib units, the original lib units. So that I think that this is quite powerful, and it helped me a lot, all the definitions that I needed, and every time that I needed to change my models. So yeah, that's base units, and we can change it. Then this is the interesting part, and I think this is pretty much the core of what this strategy is. So the first thing is to define, all the elements will be defined in the center line of the real structural element. And then I assign grid lines to whatever elements exist, where elements intersect, or where the reinforcement changes. So in this case, all the stars are the primary nodes. And those are nodes that I, as the modeler, will know where they are and what are their names. That's why there are the primary nodes and the anchor nodes. The secondary nodes will be anything that I don't know what it will be, but I will show you then how to work with those nodes that you don't know what they are. So for example, when I define the node, as I said, I need to know where it is and what it is. So my definition of the node will be all the X grid lines will be labeled as 100, and I normally go, I use the 10s to show where an important element is. So in this case, it will be the column on the wall is in 110, and then the next line of columns is in 120, and just keep going with 130, 140, and so on. In this case, in 311, for example, in this case, 310, it will be the beam, will be the frame, the moment frame in the longitudinal direction. 320, the same thing, and all the rest will have numbers in between. 311, for example, in a particular case is where the reinforcement changes. So that's why I define those points. Now, when I read the node, I know where they are because it's just intersection of the floor plan and then the elevation. So I know that that node is in the intersection of grid line 101 with 310, and it is at level 201. And that's the way we can know where it is and how it is. And in the same way, since I know where my support nodes are, I can fix them with some fixity condition, whatever it is. And now the secondary elements, and to explain how the how the elements are defined, and therefore the secondary nodes, I will use this simple example of a 2x1 bay, one-story building or structure. So what I would like is I have 4 columns in the perimeter with a perimeter beam and then a beam in between. I have a slab that is 100 millimeters on the left and 120 on the right. This is just to make a point soon. So the first thing that I will do, I will define the nodes, and I will label the nodes, and I will define those manually. Well, obviously it will be inside a loop or a for or a while, but I know where they are, I know their names. Then, when I define, I need to define the finer mesh elements for each zone. So in this case, since I know that what I need is a beam, and then that beam has to be connected to the slab, then the most critical element probably will be the slab as well, because of the formulation of the shell element in comparison to the formulation of the beam. So the first thing that I do is I create the shell, and the shell will create, it will be a procedure that will generate the shell, and the shell will create the nodes. Then, once I have that, I define the beam column elements, and now the beam column elements are simply defined in between the existing nodes. So I don't have to worry anymore about new nodes unless I have something strange. And we will see a case where I need new nodes after defining the shells. And then I define the beams in the other direction, and then the columns. And then my model is completely defined. Now, in order to make this work, I have some base procedures and then modeling procedures. For the specific case of the shells, I have the base procedures are filter procedures. So, and that's the way we will work with nodes that we don't know where they are. So for example, I can say filter all of these kind of nodes, and the OpenSees will go to the domain, will grab the nodes that are that zone specific, and it will return it to me. Then I will sort those nodes in the right order, as I mentioned at the beginning, for the local references of the elements. And once I have that, I can start drawing or defining my elements from the closer to the origin to the further from the origin. So all of these filtering and sorting procedures are the core of everything that will happen. And then the procedure mesh shells will grab those nodes and will define the shells. So it is quite similar to what the built-in command block2d does, but the difference is that block2d, for example, if I define 2 separate schemes of shells, what it will do is it will start labeling with nodes, so 1, 2, 3, 4, and then 4, 5, 6, 7, 8, and it will keep going, and then when that is finished, it will take another one. But these 2 elements, they don't share any nodes. So they are not connected. And that's a limitation that I found with block2d. So one of the possible solutions was to use an equal-DOF to link these 2 nodes. But I ended up with tons of nodes that I don't really need. So the mesh shell, what it does, it creates the same scheme as block2d, but it will compare the new node with an existing node. If an existing node is in that place, then it will not create that node. So for example, in this particular case, the mesh shell will create node 2, node 3, and then node 8, 12, 16, all the ones in between, but not the corners and not the shared ones. So in that case, when I use the same procedure, mesh shells, for this shell, it will try to generate the node 21, but it will compare it with another node that is in the same position, which is node 4. And it will say, okay, I will not generate that. But actually, there is one extra node there that is one of the anchor points of my model, as we could see there, which is that model, that node there. So it will not create the node 4, it will not create the node 21 because there is already a node there that is at 110, 305, 201. And that's the way that procedure works. And that way I ensure continuity between all the elements and connection, the appropriate connection between all the elements of my model. Then for beam column elements is exactly the same idea. The beam column element, the meshed beam column element will say, I will tell them the procedure, define a beam column element with specific properties from this node to that node. So the procedure will go to the domain, will filter all the nodes that exist here, will sort them in the right order, and then it will define beam column elements between each node, so they are all connected and there are no orphan nodes. This is a pretty interesting case because as we saw at the beginning with the way the building is seated, so the double T's are seated there, but they are not continuous. So actually they have a pin connection there. It cannot transfer moment in M3 moment. So I didn't find any easy way to define that in OpenSees. So what I did was I created a procedure that is called pin beam column elements. And what it does, it will release the moment in that end while keeping all the rest of the connections in this line and the shells safe. So the way it does it is it creates a new node that is overlapped with existing primary node there in this case. But the interesting thing is that it will label it with a -1 in front. In this way, I know that I will never ever touch a node that is already defined. And also I can use that negative tag to fill to as a feature for my procedures. So then I will draw something. Well, at the end of the model, I need to check that there is no unwanted zero length element or overlap nodes. But in this case, it's really hard to catch when you have an overlap node that you want and when you have an overlap node that you don't want. So in this case, you will always know that if it is a negative number, it's a negative tag, then it's something that you created because you needed it. So that's a really cool thing for the filter nodes. So I would join the node 6 with this new created node that is not connected to anything else. And then I will use an equal .dof to slave this node to the master node. Just as you can see at the bottom, just in 1, 2, and 3, which are the displacement degree of freedom. And that's the way I can connect all the double T webs to the main frame beam without passing any moments through it. And then same idea with
I'm just trying to
increase that.
Yeah. Sorry. The options. I don't know.
Yeah, that's enough. Sorry. So the last thing in terms of elements in secondary nodes is, well, in zones that have a lot of displacement or variation in displacement, have gradients that are really steep, I need a really fine mesh, for example, close to the wall ends. But for this particular building, for example, close to the columns, maybe I don't need that fine mesh. So in order to make the model more economical, I needed to create a shell. I needed to create a way to join 2 different mesh sizes, because as I said, I cannot just connect that node to that node and then this node to this node if all these 3 nodes will be flying free. So the best way that I found was this discretization scheme, in which I can connect all the nodes, and there are 3 elements that are a little bit irregular, but they do the job. So I needed to create all the shell on one side, all the shells on that side, all the shells in this side, and then stitch them together with this join mesh that you can see there in that trial building that I created to analyze and see how these work. And finally, I created just in case, I created a function, a procedure that checks for any orphan nodes that could be flying, could be that they were created and they are not connected to anything, so they cause problems. So those are all the procedures that I have to create everything that I need, and that was enough. Then the next part is loading. As I said, it's really difficult to load this structure because we don't really know where all the nodes are. And what I want is I don't want to calculate what's the force per level and then apply it in one point or at the end of the beam or in the center, sorry, at the end of the wall or at the center of the wall, because I'm forcing the model to create huge stresses. So the best way is to apply a uniformly distributed area loads. In order to do that, I use the same filtering procedures, and I created 2 additional procedures in which, for example, for the case of node 5 in this example, I will grab this shell element here, and I will calculate the tributary area of that shell into that node, and I will apply that load directly into that node. Then I will repeat the process for this shell, and that shell. And then I will end up with a node that is properly loaded with just a tributary area that corresponds to it. And that will repeat for every single node of the structure. So in that way, filtering the nodes and then running all the nodes through these procedures can ensure that the load is appropriately defined and assigned to every single joint. And the last part is the analysis. So last time when I saw the presentation from Dr. Ching Lu, it was pretty cool to see that I tried the same things and I failed in all of them, except with UMF pack, which is the one that I've used always. And the constraints is transformation because they were the only ones that worked. So I was really glad to see when Dr. Lu showed that it was exactly what I was using. Then, as I mentioned, with the challenges, I think it's quite difficult to have all that really long piece of code that is static, it's hard-coded. So to improve the readability, I wanted to create a dynamic adaptive solution. And I played with 3 things for my convergence. I played with the integrator, changing the incremental step. I played with the algorithm, and I played with the test tolerance. So these, for example, are the options that I provide to the procedure for different incremental steps. So I will start with 5mm incremental steps, and then I will modify that to a half, 1/5, and so on. And I can apply any number that I want here. In some cases, I even apply 2 or 4 just to go away from the main nonlinear part that was causing problems. And in terms of the algorithm, for me, it worked quite well, the Lateral-Loading method. So that's the one that I normally use for everything. But in the cases that when that algorithm failed, I just selected the algorithm number 10, 14, 4, 8, and 1. I will show you that in a minute, what that means. And then in the case of the test, I try to loosen the test times it by 10 and then times it by 100 to see if I can make the solution. So in order to make this work, I needed a modular counter, which is the one that is defined at the bottom of the page. That modular counter in this case, it will have that form. So it pretty much says that I have I haven't used any of the possible solutions for the integrator. I haven't used anything for the algorithm, and I haven't used anything for the test. But when that fails, when my first step failed at some point in the model, then that counter will go and will increase 1 in each one of them, which activates the counter. And then I will change the integrator or my integration technique, approach. 1 for the second. I will take that one. So that will be 1, 2, 3, 4, and 5. Once that finished and tried all the integrators, then that will roll and it will go 1. But then I change the algorithm to the second algorithm that I have. So reset the integrator and select the next algorithm. And that's the idea until I use all the integrators, all the algorithms, and then I start using the test, which is the first one there. And then it keeps going until it gets to the end, in which the counter will look like that. And that will be the last try. In this case, with the amount of options that I put there, I could try 76 different techniques or approaches to solve the convergence issue. If that's not the case and I still fail, the counter will turn into -1, which will indicate that everything failed. And now, having these 3 procedures and the counter, all that static code to address the non-convergence will be changed by these 3 lines of code. They're obviously longer than that, but this is just that idea. You will have 3 lines and nothing else, and they will be in charge of changing and addressing the non-convergence in the way that you propose. So now let's go to challenges part 2. As it was mentioned as well by Silvia Manzoni and several people, including Michael Scott as well. When you go with big models, you start having a lot of stability issues, especially with materials that are quite fancy. So, for example, Concrete 07 and Concrete CM. Also, I had a lot of problems with the zero length section. So I ended up using Concrete 02, Steel 02, and linear elastic shear and torsion, because it was the simplest thing that provided good results. And we will see the limitations of this model at the end, because we have to recognize that it has assumptions and limitations, and we have to use a model within the realm that we are allowed to. The second thing is, the second challenge was work in a Linux-based environment for the high-performance computer facility in NESI. Because there is only a Mac version for OpenSees and a Windows version for OpenSees. That means that you have to compile OpenSees for the specific distribution, Linux distribution that you have. And I didn't do that, but the problem is that, as we will see in the next slide, despite OpenSees as open source software, there are contributions from different people around the world that are not necessarily open source. So that was a big issue for me. Second thing is that you don't have any GUI. So as I mentioned at the beginning, I was working with OpenSees Navigator, but then when I went to the NESI facility, I couldn't use it because it was just a command line. So I needed to just create my model in Navigator, export the TCL files, and then submit the TCL files. But that was really slow. And that's why I started doing the model manually and trying to use all the powerful capabilities of the programming language. And the last thing is that every time that you send a model to NESI, you have to estimate the time that it will take and the RAM usage that you will have. And that's not necessarily, it's not easy. And if you get short, the model just stops. And you could lose, I don't know, a lot of time and a lot of resources. So to avoid that, what I created was I normally try to run molds in my computer overnight or in my laptop, something that I could just leave it there working. And I created a small program in Python that it measures the RAM usage over time, and that's a plot that you see on the right hand side. So those are either 3 modules or 1 module, and that's the way the RAM usage of my computer was used in time. So you can see that I ran modules that took 140 hours. That are really big, and then using about 50 gigabytes of RAM memory. So this was a really nice challenge because it took me to a place that I was not comfortable with, which was working with different computers and resources and time. And it was really nice to see that it could be solved. It could be, and then you could just reuse that constantly. So you can have a grasp on how your models work, what's their performance, and what are the resources that you need. And this is just a screen capture of saying that I need to use 7 gigabytes and 10 gigabytes, sorry, 7 minutes and 10 gigabytes of RAM memory. But these are not related. No, these two are not related. They're just examples. This is the part that I was just mentioned about materials that are not available. So since I wanted to use shell elements to model the concrete, and I wanted to use lighter shell elements, I needed an n-dimensional material to represent concrete. When I worked in my computer, my desktop computer, I could use a plain stress user material from the lighter shell element because I was using a Windows version of OpenSees. But as soon as I submitted that script to the NESI facility, the message here appears. So PSU mod not defining this version, source code restricted. And then I started investigating, and the thing is that the answer is that element, that material is actually not released. So if you don't have the Windows version released by the OpenSees creators, the OpenSees webpage, you will not have that material. And that means that you will never have that material for Linux-based high-performance computing facilities. And then I tried to use damage2p as well, which is another mode to represent, to simulate concrete. And well, the message is there. Sorry, damage2p source code not available in this version. I've tested. I have here in my collection OpenSees 2.44, 4.6, 2.5, 3, 3.3, 3.1, 3.2, and 3.2.2. And the only one that seems to have that model is 6.5.3.6. The revision, sorry, version 2.5, revision 6.5.3.6. The only problem with that model is that that specific version of region had a bug in which every time that you use a shell element, it prints to the screen some results from the shell element. And that was extremely time consuming, and I was not able to use it. Another material that could be used is Durga Prior, but I couldn't make it work well, so I just discarded it. So I needed a high performance computing facility to run my molds because of the size they were, the amount that I had to run. And the easiest way, well, the way that after a while, because I tried to go to design safe, tried to get the source code for the NESI facility, but it didn't work. And then the Center of E-Research at Oakland Uni, they can create virtual machines running whatever operating system you want. So they created a virtual machine for me running Windows. And that meant that I could use the Windows version of OpenSees. The only problem was that for me to use that, they had to log a lot of resources just for my virtual machine, which is against of what we do when we have high performance computing facilities in which all the resources are there and you request what you want. But as soon as you release it, they go to other people. So I had to take those resources and log it just for myself. But that's a workaround to this problem. Then another challenge, once the model is complete, we do not normally, we don't care about torsional stiffness when we're working in 2 dimensions. And when we go to 3 dimensions, we have to start worrying about it. And the first time that I ran my trial models just to start testing, because that's another thing of OpenSees. It lacks a lot of documentation. And it's a fantastic software, but if you want to know how to do something, you have to do trial tests, trial runs, trial structures. And it's pretty cool because you learn a lot, but it takes a really, really long time to really know what you're doing and why that thing happens specifically. So the first time that I did my models, I read in the wiki page that says that GJ was optional, and actually the default was no torsional stiffness. So when I read that, I said, okay, torsional stiffness is 0, so it won't do anything. But my surprise was that it was actually torsionally stiff as this model here. And that happens because when the wall, well, that's probably I should say, the blue ones are columns, then the magenta one are the shells, the green, light green one are beams, the red one is the wall, and to represent the length of the wall, I use a rigid element, which is the black line. So when that wall bends, the beam goes with it, and what happens is that you have a relative twist between the end of the beam that is attached to the wall and the end of the beam that is attached to the perimeter beam. So if that element is completely stiff against torsion, what you will do is that you will end up coupling all the responses of all the 2 sides in this trial building. And that's why it has that deformation that follows the deformation of the wall. As soon as you start defining even the 100% elastic torsional stiffness, you get immediately better results. And then there is not much, I couldn't find much guidance on this topic because you can find effective inertias for shear, for bending, but there is no ASCE 41, for example, or the New Zealand assessment guidelines. They don't have any value for what's the torsion that we could expect in a real building so we can assess it. So based on some values, I defined that 25% of the elastic torsion was enough. And that's what I work with. That torsional stiffness obviously doesn't affect much when you have longitudinal beams. They affect more when you have perpendicular beams to the wall just because of this effect. So this is quite interesting to see in modeling. This another is a really important one. It's a huge challenge. Since I use shell MIT C4, and that has a bilinear formulation. So that means that I need a lot of elements to represent zones that changes rapidly like that. When I have larger elements, the response is stiffer, and therefore what I saw was more coupling than the one I was expecting. So I think this is a must. If we use shell, you have to do a sensitivity analysis to see what's the size of the shell that is appropriate for your modeling. It's not too expensive, so it takes a really long time, and it's not too coarse, so it gives you bad results. On the table is some of the trials that I did. So mesh size of 2 meters, 1, 50 centimeters, 40 centimeters, and then 25 centimeters. The number of elements that each model had, and the time that it took to run those elements. So to run those models. And this is just a 10-story building, 16 by 16 footprint building. So it was not a complicated building or something that had something really weird happening. But you can see that even this simple building running non-linear, of course, with a mesh of 0.5, it takes 4 hours or 9 hours, depending on the orientation of the beams. with respect to the wall. Obviously, 0.25, it's way too small, and run a simple model in 140 hours, that's crazy. Not recommended at all. This is really nice. It's when the models exploded, or I don't know why that happened. Well, you see that there, you have that bending. It's because of the torsion. Those beams were stiff, but this building could get to 1.6% drift and then exploded. And that's a solution of the system. I don't know how, but I think it was pretty cool to see, and that's why I put it here. Now the problem is that you cannot see the deformation in OpenSees because OpenSees doesn't have a GUI. So it's really important to be able to see the deformation, and that's why I think in these recent years it's really cool that a lot of really good softwares have been created, like STKO, ESYS, GID as well is used. I think it's pretty nice because as soon as you see something like the building on the left-hand side, you know that something's wrong. And definitely on the right-hand side, if the thing explodes, of course it's wrong. And then the one in the middle, it happens something really weird in the first level, it drops. So it's like, I don't know what it is or why it happened. Obviously, when it happened, I just started changing parameters, but I did these things a really long time ago. I don't remember what it was. But whatever means you have to see the building deformation, it's really good because it helps you a lot to see what's going, whether it is doing something that you expect or not. Now, that part was the challenges. The second part of the challenges, and this is more or less the way I solved. Well, I've told how I solved this part. Well, I didn't tell how I solved this. So when I started, I didn't have wonderful software there are today. So what I created was a procedure, or two procedures, one in TICO that saves the deformation of every single node and the element that those nodes belong to. And then I created a function in Python that plots a three-dimensional plot. So that's what it is. It's nothing else than a three-dimensional plot in Python. And that's the way I could do that. And then obviously I just did the GIF files by just joining the pictures. So now when you start having a lot of elements in your models, it's really hard to keep track of everything that you are defining. And that's one of the, at the end of the presentation, I have some recommendations, things that I've seen, things that have been useful to me and that I wanted to share with you just in case it's useful to someone. So having Excel spreadsheets to define materials, for example, it's really cool because you can have a specific curve and then you can adjust the curve of the material to that specific curve in the best way possible. So for example, in this case, I had a concrete curve that was the orange one or yellow one. And I just, by tweaking all the variables, I get to the blue one, which is concrete 02, and it's pretty close. And then that was what I loaded. Same thing with fiber sections. I know that there are a lot of scripts to define fiber sections, but the thing is that I really miss, in all of those scripts, I really miss the graphical features. Because I could define, and well, it's about why this node is here. I can define my fibers in the best way I can, but if I cannot see an overlap figure or what my section is and where my reinforcement is, I cannot be 100% sure that I'm defining the right thing. In this particular case, I just misplaced my fingers, and I ended up having a fiber section with more than 10,000 fibers. Obviously, I didn't realize because it was all code at the beginning. But every time that I submit that model to the high performance computing facility, that error appeared. So segmentation fault, core down, and everything was gone. Couldn't save anything from that run. And every time that I run the same model in my desktop computer, I got an MKL error, which is something related, according to what I could find, was something related with the processor. So that's way further than I'm comfortable with, and I don't know what's going on there. But when I realized about these, obviously I take all the zeros off that were more than the ones I wanted, and then they started running all good. And then I did several tests trying to find what was the cut. And it depends on the model, but it's normally when you have a fiber section that is more than 10,000 fibers, you will have this type of errors. So I hope that helps someone, because I was stuck like a month with those models. Oh, I don't know why that's okay. So yeah, this one is for walls specifically. You can use it for beams as well, or columns. This one is for round columns. So it's pretty much the same idea. The cool thing about all these three things that I've shown here is that since it is Excel, you can just copy that cell there and paste it into a TICL file, and you will have the whole section. So that's for columns. And then this is for layer shells. And this one, the final layer shell is kind of painful because you start stacking all the layers bottom up. So you have to find it in a proper way. And then for example, every single piece of concrete, what I did at the beginning was that I didn't discretize that block of concrete. And the main problem with that was that I had sudden drops. And since I was working with everything, all my elements were non-linear, that sudden drop was really, really hard to solve. And I had a lot of convergence issues. And that's why once I have the gross layer, I have a specific mesh for each layer. So I can have smaller layers. It's the same thing as a kind of a fiber section. So with smaller layers, I could have smoother responses, and therefore I improve the time the model ran and the convergence of the model. And this is again the only thing that once everything is defined, and then you go to where the section is, you copy and paste. Next one. And I would like to show you exactly that. So. So let's say that we have that section, and we define that section, and now let's say that I want to move that a little bit. Let's say 25, so that will move 45. So once I have my section and I have the visualization that I want, I'm defining that this section is 100 millimeters thick, and I have all of those elements will be rounded at 2 digits. And then I want a multi-line. When I paste this command, I want it to be a multi-line. So if I copy that and then I go to my notepad and I paste it, it pastes the whole section. And in a multi-line way. So that's how easy it is to define a layer shell section with a spreadsheet like that. We can do the same thing, but instead of having a multi-line, it could be just a one-line thing. So Ctrl+C, and you will have exactly the same thing. Those two are the same, but it depends on what you like to see and how you like to see it. In particular, I like that way because I can see where all the layers are and whether they are concrete layers or steel and in what direction they are. And that is the same idea for, let's say, for example, that's a beam. So I have overlapped the two things. And if I say I want an offset of 50, well, I can see that I'm taking that reinforcement off the section. So once I have everything, I just copy that cell, paste, and I have everything again. The only thing that I need to be worried about is to delete those quotes, but then all the section is there. And an additional thing is that since you have these spreadsheets, you define one model and you can save that spreadsheet, save with definition that you already did. You don't need to just overwrite and overwrite. Because many times I did that and then I wanted to have something that I already did, but I already changed it. So now I document every model that I do in this way, and I just copy this one as many times as I need. And I think for me, it has to be the easiest thing to do. Now, as I said, when we model, we make simplifications, especially when you go with beam column elements, for example, shell elements, or anything like that. So it's really important to know what your model can do, in this case, what my model can do, and what it cannot do, when I can trust on the results, when I cannot. So that's part of the assumptions and limitations. The first part is that I'm not considering solid structure interaction methods. And that's a huge one. Every time that I model a building with solid structure interaction, many times it's a lot of the change that it generates in the system response. So in this case, in this particular model, I'm not considering that. Then I also considering that all the elements are fully anchored in the ground. That means that it's not foundation uplift, and therefore I can just pull the columns as much as I want, and I can make them fail, and the model will do that because that's what I'm defining. So I need to be sure, I need to be careful with what's the maximum tensile force that I'm allowing in my columns, and whether that is realistic or not. Then something else is that the beam column elements and shell are centerline representations, and that's a really important one, especially for floors, because when you have double T units, you know that the center of the neutral line of the whole system is in a different position, but both of them, the slab, the shell elements and the beam will be defined at the same level. So that's something important to know. I try to change the fiber sections, and I define them offset. So as you saw in here, I can provide offsets to the sections. So for example, I can provide an offset of 200 there, and the section will be defined with an offset with respect to the center. But what OpenSees does is that it returns everything to the center of gravity. So it will calculate the center of gravity of my section that has the concrete in one part and the reinforcement in a different part. And whatever the center of mass of that system is, that will be the center line of the model. So I couldn't really modify it in the way I wanted. Then, having said all these, and given that I have linear representation of shear and torsion, this model is represented with flexure dominant buildings. So that's what I analyzed. Then there are some assumptions in the way the wall and the floor are connected. In particular, I think I assumed in my model that since I wanted to capture the effect of the out-of-plane stiffness of the floor and how that couples the wall and the columns, I consider that my wall-to-floor connection was perfect, and there was no punching shear failure in the corners of the wall, which probably will not happen in the real building, but it was something interesting to see in this research. What could it be if that failure doesn't occur? Then I also assumed, based on a previous research from one student here at Oakland, that the double T unit flange works in conjunction with the topping. So that's just one solid slab. It was, I think, about 150 millimeters of slab. Since the beam column joints of the frames were in the perpendicular direction of what I was analyzing, I didn't consider any type of joint deformation on them because it was not really relevant for what I was doing, because the load was not in that direction. Then based on all that, I checked that my building was able to displace up to 1.5% lateral drift. That was well before the onset of any failure or strength degradation of the system, but it was far enough to fully activate all the mechanisms that I want to study with this building. Now, this is the way the complete building looks like. It has fiber-based distributed plasticity with force formulation for the walls and displacement formulation for all the columns and beams. All of the elements have a Lobato integration scale that use between 3 to 5 integration points. And the floor system was composed of layer shells using shell MITC4. This building has 65,000 elements and 42,000 nodes. And this was, the nodes are that small, if I can say that, just because I didn't replicate or didn't overlap nodes that were not necessary. In this particular building, it was a test building to see how it performed, to check connectivity, check that the mesh working. So for example, that zone there close to where the walls are have a finer mesh, and then all the center portion has a coarser mesh. So there is a line there that connects both of them with that scheme that I showed in some slides before. This took 45 minutes just to assemble, 1 hour to load all the elements and run the analysis, and then 4 hours to run a pushover analysis to 2% lateral drift. And since I was running this in my model, I didn't want to have any convergence problems or any excess RAM usage. So I defined all the elements non-linear with fiber sections and layer shells, but all the materials that were assigned to those sections were elastic. So it was essentially elastic. Since it took that long for this whole building, plus another considerations, we decided that it was not suitable to run all the amount of models that I needed to run for my PhD with this building because it was too big. So what we did was we reduced the size to just one slice of the building, which is where all the interesting things happen. And we provided support conditions all around so the building behave, or these slides of the building behave in the best way possible, as close as possible to the full building. It was the same idea, but the model was reduced to just 23,000 elements and 15,000 nodes. It took 10 minutes to assemble, 35 minutes to run the gravitational analysis, and up to 80 hours to run a monotonic pushover analysis, and up to 170 hours to run a cyclic pushover analysis. So most of these buildings, I just send it to run in the virtual machine in the center of your research, and I waited a week, and then I came back and just grabbed all the information. Both buildings, these buildings were run just up to 1.5% lateral drift because of the reasons that I already mentioned. In terms of RAM memory, it normally took around 15 to 20 gigabytes at normal ranges, and then it had sudden peaks at 40 gigabytes. So I ended up requesting something like 256 gigabytes to run 11 models at a time, and that was okay. Some responses, just to, this is the part where I'm just showing some cool things that I think are an output from my model based on all the modeling that I did. These are the columns, these are the moment and the curvature for the columns that are right beside the wall. This is for the column 320, which is in tension because the loads are in positive Z direction, which is going down the spring. And the column in 330, which is this one, is under compression loads, again, because of the load. So we can see that the moment diagrams are linear, which is expected. They have the expected shape as well that they have. And then the curvatures, this has higher curvatures because it's subjected to tensile forces. Well, this one has smaller curvatures because it's subjected to increased axial forces. And actually, this one started developing a plastic hinge at the base. So that was something that I was expecting to happen more or less because of the way the loads are already distributed. In terms of the wall, it can be seen that the wall has a moment diagram as a dual system. Moment when you go to any book and you see dual systems, you will see that the wall has that type of moment in which it's not from the top right to the bottom. It has this type of belly and then changes its moment. And that's a curvature showing that most of the deformation was actually developed in the plastic hinge in the first level of the wall, which is what I expect this building to do in an earthquake. Obviously, since I'm using fiber-based elements, I need to check localization. So I check this wall for localization issues with 3 integration point 4 and 5. And the middle part, because of the weight of the integration point changes, that tends to change. So that's non-localization, it's just a different weight of integration point. But the one that is closer to the end, in the 3 cases, they predicted pretty much the same. So this wall was free from localization issues. These are the results of the wall-to-floor interaction. So in terms of the building response, for this particular case, these are just some selected results. It's not all the results. There are a lot of more results. I'm comparing 3 buildings. It's the same slice building, but the red curve doesn't have a floor system. So all the nodes at every single story, they are connected with an equal DOF command. So all of them move the same in the plane, but they don't have any contribution of the coupling between different elements. The green one is the model as it is. It's the closest I could get to the actual building behavior. And then the coupled truss, the blue one, I changed the columns to be double pin, which is something that it's not that far-fetched when we design buildings in practice. We just assume that the columns don't contribute anything, they are just gravitational, and that way we attract more loads, so we think we attract more loads to the wall. What we see here is that the building is, the coupled building is way stronger than the uncoupled version. So the slab has a huge role in the building response. And then assuming that the columns doesn't contribute in terms of moment and shear, they just contribute gravitational forces, it makes our building weaker. So we have to consider that our building is a little bit stronger even when we assume that. The good news is that if we see the wall response, since the columns are not contributing at all the walls have to take everything. So actually the blue curve goes beyond the green one at about 75%, sorry, 0.75% drift. And then that's a result of the cyclic pushover. It's pretty much the same idea. It follows the same logic in terms of the building response. For the wall response, we can see that the shear that the wall receives in the coupled cases are way larger than the uncoupled case. But the moment that the wall has to receive is the same, which is something as well that we expected, because the columns will only generate outrigger effect that will contribute to the moment capacity of the building, but not the shear capacity of the building. So all that extra shear that the building can take, because it is stronger against moment, it has to be resisted by the wall and just by the wall. And then on the right hand side is the axial load variation of the columns. Those are the columns, that column, the wall, and that column in the same order. And you can see that the wall varies a lot of its axial load. It goes from, in the blue case, it goes from, it changes like 100, I think 70% is the number. It's 70%, it has 70% more axial loads, which will have a huge impact if you are designing these walls using, how to say, I forgot the name. Using ductility, ductility. Same thing happened with the columns, and the columns even go into tension. So they all started there. So the red line is a really good point, it's a marker, because it's the axial force that every element in the uncoupled model have. And that means that that's the base for everyone, for all the loads. And the wall goes up and down the load. Same thing with the columns. The columns have way larger variations. And then I mold the wall. Sorry, I mold the floor. So this is like a contour map of the floor, and the red one is the wall plane. And the further away I go perpendicular to the wall, I have less formations. This is the two at the top are the coupled model, and the two at the bottom are the coupled truss model. You can see that, for example, in this case, this column here, they have all the moment capacity of the columns, and therefore that column will try to counteract the rotation that the floor wants to have because of the wall is lifting that part. But in the coupled truss model, in which the columns are just double pin, I don't have that moment against that rotation, and therefore the floor can rotate as it wants. And on the right hand side, that's the elongation of the wall. So this is what happened at level 5 at the end of the pushover, of the cyclic pushover analysis. And because of plastic hinge elongation, the wall actually gets taller. In this case, about 30 millimeters taller, or in both cases. And I think this is the last part. I have 2 more slides. These are notes and recommendations that I've came across doing all these models. I had the first one there is because it took me a really long time to find how to make node reactions work. And the only thing that it needed was, before calling node reaction, I needed to call reactions, and that's all. In your code, you put reactions, and then you call node reactions, and you will have everything. In particular, I use that to check that my gravitational force was properly applied to the model. Then another recommendation that I like is that at the beginning, I started going with material tag 1, material tag 2, material tag 3. But then I wanted to have all the concretes together, all the steels together. And I couldn't, because I already had defined progressively 1, 2, 3, 4, 5. So what I do now, after a while, is that I reserve tags, and that way I avoid confusions. So for example, all my elastic materials will be defined from 1 to 99. And probably I will reserve the same thing from 1 to 10 will be one specific type of material, 10 to 20, or 11 to 20, a different type of material. So I will complete those gaps in the meshing when I need it. Same thing with the section definition. Whatever is 100 will be a lighter shell. Whatever is 200 is an elastic shell, and so on. That helped me a lot. Then I strongly recommend that everyone who runs OpenSees use a log file. You just call the log file command, you give the name of your log file, and you have everything that you need. And then when non-convergence happens, you will have that the element 14,117 failed, and who knows what that element is. So another thing that I find that is extremely useful is that once you define all your elements, create an element summary. it can be done with the procedures that I had. It can be done in a really easy way. So since I know that is that number, I know that is a wall, and then I can focus on what's wrong with my wall. The next one is to use timestamps, especially if you're running things that runs over a couple of days. Many times at the beginning, I start running my models and I just have the time as it was shown here, right there. But then if you are in a step of non-convergence where nothing has been written, the only thing that you will see is that is 1 hour and 9 minutes. But you don't know when that text was printed in the screen. Was it 2 hours ago, 3 hours ago, a day ago? So you cannot know whether your model is stuck or not. So what I end up doing was that I put the time that the model has been running and when I wrote, or when the model wrote this comment. So I know that if I get to my computer and it's 11 p.m., okay, this was just posted 8 minutes ago. So the model is running well and it's not getting stuck. One that I think that is also quite useful is to avoid deleting models. At the beginning, I did one model and then I never saved that model and I modify that model and I keep modifying and modifying and modifying. And after a while, I knew that I had done something in the past and I wanted to get to that point, but since I never saved the model and I just change it and change it and change it, I had to do it again. So now my approach is I try to not delete models, especially in OpenSees. OpenSees, the size of the files are tiny, they're just TXTs. So you can compress it and they will be even tinier. So every time that you want something that you did in the past, it will be there. Or another case is many times I just saved the results, but I didn't save the model. And it was the same thing. So I got the results, I went through the results, they were really useful, but when I wanted to modify something in that model or I wanted to see how I get that, I never got it because I modified the file. So that was quite frustrating. So I would say don't delete models, just leave it there, put a name, put it into a log, and then you will have for a quick reference whenever you need it. And I think this is the last one, just keep if you work manually as I do, keep the model in separate files. It's way easier to handle it. For example, nodes in one file, elements in a different file, materials in a different file. That way you can just move that file as you wish, and that's quite useful. Oh, it was really useful for me. So yeah, that's my presentation, and that's Control-Z to close.
Awesome. Thank you, Ericson. It was really good, and just as a personal experience, I would like to tell, when I started OpenSees, Ericson actually went through some of the steps for me, and it really helped me, like in the way it really helped me to direct the way I want to do things. I mean, I didn't know much coding, but like at least once I learned the basics, okay, Ericson told me this, so I have to line up in this version. So I think if you are a new beginner or even like intermediate level, and if you have to deal with long models, I think like some of the suggestions are like really useful. Maybe it's like, yeah, we know that, but like it's really useful. And just for the last one, Ericson, maybe you can use GitHub for saving the multiple files.
Yeah, as well.
Yeah. Yes. Yeah. And any questions from anyone? Like,
not a question, Pavan, but I just wanted to say thank you to Ericson for the presentation. It was really long, and sometimes I don't understand some of it because they're far too advanced, like shell elements and stuff. I haven't really used them, but all those pointers that you gave, they're really useful, really practical for anyone, even if we're not doing 3D models or whatever. I think it was really great. Thanks, Ericson. And actually, if you can make a blog about your tips, I think that would be really awesome.
That's why we have videos recorded and posted. How do you? Oh yeah, we have a question.
Yeah,
I have a few. So maybe a few.
Oh yeah.
But maybe go with the online ones.
Yeah. Can you open it?
it says how you confirm model calibration with experiment, manual calculation, or by some other software simulation. Yeah, so in these big models, it's really hard because you can find tests like the ones that I mentioned at the beginning, 1980s US-Japan research, 2007 slice building, some of the e-research 6-story tests that they do. But the problem with those is that those models, when they test those buildings, they are so specific, they are so expensive that they need to put specific details for specific things. It's not a standard building. So it's really difficult you will spend a really long time trying to model that. And actually, the guy that was working purer than me in the PhD, his PhD was modeling one of those buildings just for that. So it's really hard to say. The best way is just trying to check that all your elements work well, that when you see your moment diagrams are correct, when you see your shear diagrams are correct, you can do manual checks, you can do deformation checks. So that's the best we can do. And that's the best I could do.
So you didn't calibrate your models with anything else?
Against what?
Okay. No, for example, you could do with maybe EDAPS or SAP or something, right? Like just
the problem is that model that I'm using. So I started working with SAP, but SAP is really good for practitioners. But when you, at least at that time when I started, when you start using non-linear materials, it's not good. Especially all the descending branches of all of these theoretic materials, they are horrible. They're really horrible.
No, but at least, for example, you can do like the calibration in elastic. So at least in then you can say like, okay, at least this we have like in this range, so we can extend it to this.
Yeah,
assuming.
that could have been. Yeah, no, I didn't do that.
Okay.
I just went with the non-linear and I checked that my materials were working well, my demands were working well, and just a lot of small checks. And then you don't start with a model, huge model straight away.
No.
So you start with something small, then you add a little bit, then you add a little bit.
Yes.
And so every step that you go through, you know that what you're doing is correct. And then suddenly you have those explosions.
Yes.
And okay, one step back to the point where I knew it was correct.
Yes.
And then take a different direction. So that's the way I did it.
Mohan, couple of questions. Oh, sorry.
Yeah.
Let them.
How do you sign with missions?
Yeah.
It does.
So yeah, it's just a sensitivity analysis. You have to put a mesh size, random over, take some samples. Let's say the pushover curve, then reduce the size. Do it again. Overlap the curves, and keep doing that until your response doesn't change much, because it will always change. But you have to find the balance between accuracy and computational economy, because you cannot be running. It would be really cool if you can have 250 millimeter shells, but the problem with that is that one model takes 140 hours, and in the examples that I put in the screen, so that's really difficult to do. And no one has that much time to do that. So it's just select different shells sizes for whatever you need, run the analysis, and see how your structure behaves and how much it changed.
So the 140 hours is like one core, right? It's like embarrassingly parallel one, right? Not that domain decomposition.
No. Just OpenSees.
You didn't try the domain decomposition because it's big model, right? That's why.
Yeah, no.
Okay.
No, unfortunately, no. The best thing that I could do, that I did at the time, was OpenSees SP, but not empty. For what? Which concrete model for the fiber elements? Concrete model for the lighter shell elements? Well, I guess I can answer both. For if you have just a single wall, because I did what I did calibrate was the elongation of the plastic flange. I compare that to tests here in Oakland and the States. And for that model, everything worked well with concrete 07. And then I had to include as well the strain penetration and bond slip using the model from Shao and Sridharan from 2007, which is a typical the bond SP material. But then when I moved to the big building, all of those elements cause a lot of trouble. And what I ended up doing was concrete 02 for fiber-based elements. I get rid of the zero length and I use, there is a guy, Oyen in 2006, he published his master thesis. And what he does, he finds a factor, an alpha factor that modifies G, the shear elastic modulus of concrete. So you can account for both the shear deformation and the strain penetration of the foundation interface. And that's what I ended up using. And for the lighter shell elements, I work with the concrete material that Professor Lu provided. So those were the concrete models that worked well for me.
Sorry, add another question. How about the concrete CM problem in your model?
It's pretty much the same thing. What happens is that concrete CM it's a better version of concrete 07. So concrete 07, basically what I remember, concrete 07 has the descending branch has 3 lines, but the full model proposed by Chang, I think it's a curved line, it's a soft line. So concrete CM, I think it does that. And it has more flexibility in the parameters that you can define, so you can match the hysteretic response in a better way. But both, as I think it was Dr. Scott that said that all of those really complex materials work really, really well when you want to analyze a single wall and you want to capture all these theoretic loading and unloading branches. But as soon as you go to a system, they don't work. And that's what I found. I couldn't make them converge at all.
Always them that I echo them. Thank you very much for the awesome presentation. First question, modeling the floors. So you had mesh, the floor, you meshed it.
Yes.
And you mentioned it's precast double T's.
Yes.
So like, how do you go about that? Like 2 floors are 1 mesh?
No, what I did was I separated the section. So you have the double T and the topping. What I did was I took the web and I modeled the web as a frame, as a line element, with the pre-stressing, because it's a really long, so I don't want the thing to start generating a lot of stresses. And then the top flange and the topping, I consider them as just one section. And that was my layer shell.
Oh, okay, got it.
But the problem is that you don't have that, you don't have that top flange with topping and web. What you have is that. So it's more flexible than this one, because this one has a larger section.
Okay.
And that's one of the limitations, but that's why I pointed out, because all the models are centerline models.
Okay. So for each web for the double T's for the floor, you had the element and then the shell, regardless, you could have in between each line element.
Exactly.
Those, right? Thank you. Going around the connection of the floors to whatever support system, whether it's a core interaction with the natural force resistance systems, whether it's a frame or shear wall, you assume it's more or less thin, right?
Yes, the web of the double T.
Yep. And that's the supporting point, right?
Yes.
Did you consider any spring or something for the contribution of the floors in a perpendicular direction? So, for example, if you have the floors panning, if you can bring up the fan, the floors panning this way, and you have frames perpendicular to it. So, how are they contributing to the rotations of the frame?
You mean that one and the frame?
So you have in this picture the floors panning vertical direction on the
Yes, like that.
on the slide, and then you have the frames
Yes.
and perpendicular to it. So for example, they even see that within the plastic hinge zone above the column, how are they contributing to the
Oh, no,
the stiffness
because
of the frame?
what I wanted to capture was a transverse direction,
Okay.
not the longitudinal. So
Okay.
I never expected
Mm.
plastic hinges to form in the frames.
Okay.
The frames were just there to, because it was part of the structural system.
Okay.
All the pushovers that I did was vertical, and well, in the floor screen, right?
Yep.
It was positive set, which is going from 310 to 340.
Okay.
And then the cycling one was from 310 to 340 and reverse.
Yep.
So I never worked. I was never concerned
Interested in
about
what happens there. Okay.
column.
So the connection between the wall and the floor, you just
Perfect.
slave node, right?
Yes.
Perfect. Cool.
Well, it's not a slave node. It's just one node that joins the shell. Sorry, the fiber element of the wall with the shell element. So it's not slave. There's no equal DOF there.
Cool. Got it. You mentioned about briefly about the loading. As far as I understood, you mentioned about the gravity load.
Both gravity and pushover loads.
Can you briefly talk to us about how do you go about the lateral loading? Because you have heaps of nodes, and
Yes,
then you have the lateral load. You mentioned you don't want to concentrate it in one node.
exactly.
So how did you distribute it?
With the same procedures as I use to
Okay.
load the vertical. So those procedures work in whatever direction you want. And the only thing that they do is they grab a shell element, and the procedure asks the domain, asks the element, what are your nodes? Once it has the nodes, then the procedure asks the domain, what are the coordinates of these nodes? And then it calculates what's the area and what's the tributary area of that shell to that node. Since you're given a distributed load, you just grab that area times by that load, and then the procedure assigns that load to the node.
Okay.
And then it does the same thing with the one that is beside, beside, and beside. And that's the way the nodes are all loaded with whatever load you want.
Okay. Cool. One final quick question. You were answering a question about the material properties, and you mentioned you captured the bond slope. How do you do that?
There is a material that is called bond STKO. And that material has it has a paper that explains how to do it. Basically, you use a zero length section element. Okay. You put the concrete material there, which has to be modified because you have to allow a lot of strains without losing strength. And then for the steel bars, you use the bond SP material.
But the plain bars, that's why you use that.
No,
Then why did you bar slip?
because all the bars have bar slip
Oh, okay, but
and strength integration. All okay.
it's not because of the plain rod bars, right?
No,
Okay,
actually, I think the model is just for the 4 bars.
okay. Yeah, I mean, I'm trying to capture plain rod bars, bond slip. I'm not using this, I was
Yes.
just, yeah.
So is that one? Is that the material? And then some part here, this is the way it works. So you pretty much define, it's the same thing as defining a steel material, but you assign it, but instead of being steel, is this bond slip. And then the concrete section has to be defined with a concrete material that allows a lot of strains without losing strength. So the rotations are generated.
One final question.
No worries.
In terms of validating your model, how did you validate? Like, how do you know?
It's
How
what we were
outside
talking
to
about. Yeah,
there's nothing to validate against?
it's really difficult. It's really difficult because, as I said, if you could have a normal building that is tested, that would be pretty cool.
Yeah.
But all the buildings, real buildings, 1-to-1 scale that are tested, they have a special thing in the wall, a special thing in the slab, a special thing in every single joint, special furniture, special blah, 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 blah. So if you want to calibrate or validate your model, you should have to, as I said, do a doctorate just modeling that thing. And that was Jonathan Watkins did, which was the PhD that he did that for e-defense building.
What's his name?
Jonathan Watkins.
Thank you.
I think there was one more.
You have,
Yeah.
you have one more?
How can I turn on the questions? I'm pretty sure that I read one.
Oh, this is the answer.
Oh, I don't know. Annotate?
No questions.
That one.
Hey guys, it's Peter West here from Whakatane. I did write a question in the chat. I don't know, is it easier for you to see that and respond to my written question, or shall I speak to it?
That's a question that I was looking at now.
Yeah.
Do you know if it's possible to get a response from the middle of the year? Yes, you can. Yes, you can. There is a recorder that allows you to do that. And I'm pretty sure I have that in some part as well. If you want, I can give that answer to Pavan, and Pavan can post it. Because
In the OpenSees forums, if you open it, there, I mean, I have answered this question there, so that's why I'm telling. For the fiber section, you can record the response at the particular fiber. If you're using OpenSees Python, then there is a set of commands. I don't know Integral.
You know, but he is asking for the layer show.
That
can be done.
But it's
I know
fiber,
it can
right?
be done. I have the code to do that,
Okay.
but I don't know where it is.
I really appreciate that, and it'd be good to hear about that. Thank you very much, Ericson.
So,
Yeah, I have another question. Could you please explain more detail about the problem you face about the stability of the elements and the material, such as zero length section or represent something else?
I don't know what causes the instability, but what I know or what I understand is that those materials, calculate every state of those materials are that complicated that when you have a whole building and you have to solve the equation, they produce small variations that can just get you further from the equation and further from the equation. So that's what I understand, and that's a better understanding that I have. I don't know why they do that, but I just know that everyone says that I face that, and I just say, okay, it is what it is.
Okay, in detail about your instability issue is what? I'm curious about.
I just didn't converge. Now, I don't know, I don't remember why it was, because that was like 4 years ago. So to be honest, I don't remember whether it was an element, whether it was the whole building. I don't remember what was the exact error that appeared in my logs.
Okay, because when I try to do dynamic analysis of my 3D model, I face when I calculate at the end, it suddenly shapes, and I think that's numerical analysis, not about my modeling. So if you, when you talk about the stability,
Have you tried to use a simpler concrete material?
no.
I think you should try to work with simpler concrete materials. Because the thing is that the way I see modeling, you can go really fancy with really complicated models. But then the answer is that necessary? Are you killing just a fly with a cannon? Something like that? Because it's a system.
Yeah.
When you have one wall, you really want to know what's going on in that wall, what's going on in that column, in that beam. But when you have a system, everything gets blurry. And it's the response of the system, not the response of the individual elements. So that's why I wouldn't go more complicated. And then you have to balance, you have to trade off things. Because if you start going with, I will model a building with strain penetration, and soil structure interaction, and the piles, and then every straight penetration in every interface in column, then the joint stiffness, then the connection of the slab to the beam. It won't work. Yeah, it won't work.
Or you need a big computer. And
Yeah, because the issue I just referred, what I try to solve it is I just change the algorithm and it has been solved. So I think sometimes that's not seems to be another instability.
OpenSees is quite particular in that sense. It has happened to me that I run exactly the same model without changing anything in a different version, and it works. I don't know what it is. It should be the same. I don't understand. So you can change versions as well.
Oh, I was thinking.
To see if it works.
So yeah, such a weird way. Yeah.
One final question. In the slide of the wall to floor interaction, if you could bring that up real quick. You had the pushover curve at the bottom left corner and the cyclic response at the top right. Yep. So at the bottom left one, for the wall response between the, I can read the coupled and the coupled truss.
Yeah.
And if you look at the same of the blue and the green on the top right one, it's actually the opposite. So the coupled. So could you briefly?
Yes, the difference is that the one on the top. So imagine that. So you are building, and you have ski poles, right? So if someone pushes you, you will go like that, and you will load this one.
People can't see.
Sorry.
People online can't see.
Every-
Yeah.
Well, the thing is that you will load one pole, and that will give you a lever arm with respect to you.
Yep.
So your system yourself is more stable against bending moments, against overturning actions.
Okay.
That means that you are stronger, and therefore you can receive more loads, because now it's even more difficult to overturn you.
Okay.
But what resists shear is just your voice, just you, not the poles, because the poles are pinned, so they cannot resist shear. And that's what happens here. So the building response is stronger. But then when I see the wall, in the case of the coupled truss, because the columns are trusses, they cannot contribute with anything. And therefore, all that extra shear goes directly to the wall. And that's why you have that behavior. Okay. So it's like an uncoupled moment shear capacity. If you would like to put it that way. Maybe I'm saying something that is really wrong, but that's a really good idea on how to explain it.
Okay. Cool. Thank you.
Any other questions from anyone? Looks like no questions. I mean, if you have any questions, you can email Ericson. And thank you so much, Ericson. I mean, it was a long session, but it was a good one. Thank you. And yeah, I'm sure it will help a lot of people who are doing the buildings and big models. So thank you.
You're welcome.
And